Professor Dave here. Let's discuss acid-base equilibria.
He knows a lot about the science stuff. Professor Dave explains.
When a strong acid or base reacts with water, we can say that it completely ionizes, or that every molecule of acid will transfer its acidic proton to a water molecule. If every molecule reacts to completion, this makes things neat and tidy. But when weak acids and bases react, they only partially ionize, and they establish an equilibrium between the ionized and unionized form. And that means we have to do some math. Ka is the acid ionization constant. This is derived just like we got Kc for generic chemical equilibria. Note that we don't include water as it's a pure liquid. In this way, Ka is a measure of how thoroughly an acid-base reaction proceeds in the forward direction. A larger Ka means more products and a stronger acid. A smaller Ka means more reactants and a weaker acid. So an acid with a larger Ka will be more acidic and therefore associated with a lower pH. We can determine Ka experimentally. Let's say we want to know the Ka for a weak acid like phenol. We can set up an icebox just like the kind we already know. We can use the pH to calculate hydronium concentration and therefore also the concentration of the conjugate base, since they are the same. As it happens, the change in initial concentration of the acid is so small that it's negligible, and we treat things as though none got used up. Plug these values into the expression and solve for Ka. From this information, we can also calculate the degree of ionization, which is the ratio of ionized to unionized acid molecules in solution, or the percent ionization, which is the same thing but expressed as a percentage. This is a pretty weak acid considering so few molecules transferred a proton to a water molecule. Sometimes, like in the previous example, the acid is so weak that we pretend the concentration of the acid doesn't change. But if it's a little stronger than that, we can't make that simplifying assumption, and the math gets trickier, but still essentially the same. We can make iceboxes for weak bases as well, or multiple iceboxes for polyprotic acids, one per ionization, just more math. A buffer is a solution that has the ability to resist changes in pH when limited amounts of acid or base are added to it. Buffers are made by combining a weak acid or base with its conjugate. In such a solution, because both the acid and conjugate base are present, they are able to neutralize small amounts of any acid or base that are added to the solution. Many biological fluids are buffer solutions because they must maintain a steady pH to avoid loss of critical biological function. The bloodstream, for example, maintains a pH of around 7.4. Otherwise, its capacity to carry oxygen around the body would be lost. Buffer solutions of a particular pH can be prepared using the Henderson-Hasselbalch equation. We know about pH, and pKa is similar in that if pH is the negative log of the hydronium concentration, pKa is the negative log of the Ka for that acid. What this shows us is that in order to create a buffer solution of a desired pH, we must use an acid-conjugate base pair where the Ka is approximately equal to the desired hydronium concentration, or rather where the pKa is equal to the pH. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.